But I had the fucking thing. Alright, so it looks I'm back. And it looks like the whole thing is working, so that we can now jump back to the fucking building. Or like, is this still okay, I'm not going to rage, it's the beginning of the video, I can't swear. This bee is not fucking to wanting to work. Whatever. Uh, I'm just using a bit of help here, cause I mean, I'm not going to use the help if this very fine PC will not load the MATLAB application. Maybe just this shit just yeah, it would be lovely. I think I'm just all over the fucking place. I can't say. I can't say a single. How do you say this meaningful fucking sentence? Ah. Alright, alright, alright. Alright. Just gonna close all these. I will need this, and if this shit would. I'm not going to swear. God damn it, man. Like. Yeah, maybe I will close these. Yeah, here I'm just going to quickly showcase this before I close all these. This is the scroll, and I have like a full assembly with the impeller. This is a blower that I have designed, I think, Wednesday. Yeah, I think it was Wednesday. Yes, this is the blower. I have already made the impeller. I designed this on Monday. Printed it out. And yep, I have assembled here, and I've made a cross section, so to speak, and to see the clearances. I've gave it like 3 millimeters of clearance here and there, so if it wiggles it doesn't like machine itself down, because it wouldn't be too good, because it would create big how do you say this, mm, mass imbalances. Yes, that's the word I'm looking for. Mass imbalances that would actually make it to vibrate even more at higher RPMs, or I mean at even any RPM, but on higher it would just completely collapse. Oh, maybe the MATLAB is wanting to start. This is not a fast process here, I guess. Or at least, whilst I am. This is the whole thing. We have like a little adapter here that makes this be able to have like a hole, because they usually have a how do you say this? Fuck, I don't know what up. Maybe just carb crash or some shit. A square outlet, because the thing is square as you can see, and I would even have a square outlet, but my measuring devices and the blower or the burner's duct is a hole. It is a circular thing, not a rectangular thing, or like a vent. So that's why I made it to circular, and as you can see that there is like a lip on both sides. I mean, there is one lip on this, and there is a negative of it on this side. If we hide this, we can see that there is a lip around all the edge. There is like two reasons that this is there. One, it seals better than just a flat thing, because the air has to come and do this rectangular. Basically, if you were to imagine it, there is a bit of excess pressure in there, so higher than atmospheric, so all the pressure from the inside wants to go out to the lower pressure on the outside, and it has to do like a complete turn, so it would go up, down, and out. Then this is longer path, so there is like a higher delta P, so pressure drop here, and basically it would not want to go that much, and it will not leak as much as if it were that. Plus, if you add the silicone sealant in between the two lips, because it is like how do you say this, maintenance friendly, in the sense that you can basically take the two parts apart. And if you take like a knife and cut here, basically if you put the silicone to this rim or to this lower thingy here, I hate this that it wants to like highlight it all the time, but if you put the silicone to this side here, then when you put the two parts together and the screws tighten it together, the silicone would be basically pushed out that way and this way, and basically that would mean that if you didn't have this little edge here, then the silicone would protrude into the middle and creating disturbances and basically like a reduction in flow. So this is basically a very efficient way, so that you can just basically put your knife, Tanto knife or whatever little schnitzer here, and you can basically run it along the rim, and then you have the cut, and then you will just need to seal it back if you glued it together, and maybe just need to take it off, peel it off if you can, and then you can reseal it or whatever you want. So this way the silicone won't push into the inside and creating a big disturbance in the impeller, reducing the total carried volumetric or mass flow, which one you prefer. It's the same basically. So that's why. And the third reason is that it basically helps to center the whole thing. If we have the two parts, oopsie. So if we have the two parts, this basically centers. There is a bit of gap here both on the top and the side here, because there is like, I think it's 0.3 millimeters. I usually round with 0.2, but I have given this 0.3 so that it has a bit of like a wiggle in there, because 0.2 seems to be very tight, and there is always like a little debris after printing that you need to clean up manually with like a schnitzer. But hopefully this way it will not get stuck, and I will not need to like machine it, you know, with like repeatedly have to cut material off of it so that they fit together. I think maybe this will fit a bit more loosely, but I think it will still position the two halves pretty well, like compared to just having two halves that are flat to each other, and good luck with positioning that. So yeah, the other way is to use a like hose that you put like little cylinders into, basically like pins that they call them locating pins or something like that. Basically would take like 3 or 4. With like a rectangular thing you would be able to do it with 2 basically on the opposite corners, and that's it. For like a center thing you would need, I don't know, maybe like 3 or 4 to basically one here, maybe one here, one here, one here, or maybe 3. So one here around, one here, and one here. Yeah, I think with 3 we would be able to locate it, and then you could screw it together. That would work as well. But this rim here is like a very sweet thing in that sense that again helps with the sealing, creates a higher restriction for the air to go out, even when it is like unsealed with when there is no sealant. And the other thing is that it helps you to not be able to put the silicone in. I mean, the silicone will still go in if you overdo it, but this way it is less of a problem if you apply the silicone in a, how do you say this, thin layer, I would say. Yeah, you can overdo it still, but it is harder if you make it thin. So yeah, this is the thing. I will close all this so that I can run better on like lower computing power, lower needed computing power, because this shit is just not wanting the fucking work. Yeah, this PC is not it. I really hope my stream is still going. I don't. Yeah, it's still going alright. cause maybe it just fucking froze last time. Show will close all this bitch. Right. Let me fucking do this. Not a fast process, is it? So you can't even start. I mean, now I can actually do it properly. I really hope that alright, there is no sound of the desktop, so I'm not going to get like sued for using music here. Alright, closing these, close these. Yeah, as this is the measuring device of the blowers. I will have to make a reducer, so basically this this is replaced by another one, which is going to be a smaller one, reducer to a smaller diameter, because this is 57 in inner diameter. I think this is 45. Maybe I should have done this with a bigger diameter. 45. Yeah, I could have done it with bigger one. I could have done it with a bigger one. Whatever. Whatever. I'm going to put a adapter to it, so it basically expands to this. And there's this orifice plate here that I have made. This is basically done already. It is assembled, it is sealed around the edges. I don't think it's sealed here, it is connected to the old blower. But I will be able to measure the pressure drop. There's two of these little things here. Here's one that as well, but it is cut. Now on the model, and I have inserted copper pipes here and glued them with 2-component glue, so that I can take the pressure readings from there, pressure data from there, and I will be able to compare them with a differential pressure sensor, and basically able to with like formulas I will be able to calculate out the volumetric flow, meaning the cubic meter or liter per sec values of the blower's output. So it is the carried volume of the blower versus the power that it has basically at 50% duty, meaning that it is 50% on, or like half, you know, it is going on half power, or 75% power, you get the point. So I will be able to measure those values out, and with those I will be able to design the burning chamber of the whole burner. Otherwise I will not be able to just get, I will be able to guess, but guessing in like engineering is not a fucking option. You need to measure everything, so you know exactly what is what, because otherwise you wouldn't have cars, you wouldn't have fucking planes flying in the air, you would not see jack shit in life, because then nothing would be just designed but like made, and then you would have shitty things, not even to mention that they wouldn't work either. So yeah, this is why you need to measure things, but to measure them you need to make these like auxiliary units or things, devices you need to measure with, which is another difficult thing, but I guess that is required if you want to build things rather and design them, rather than just build and be like a normal fucking maker who does no fucking designing beforehand whatsoever. I mean, on some level, sometimes, because this wasn't actually designed to and iterated through trials and tribulations, through CFD simulations, all that, because I don't care that much about the output of this. This is going to be pretty good. I don't care if I produce 5 to, I don't know, 10% more volumetric flow at that point. It is 80% there. but with the burning chamber I will do care. Maybe with this, if I will need a better blower, and then I will redesign it to be able to have a higher efficiency and all that. But to a burning chamber, which is going to be like to how do you say this, like most important, not most fucking important, then yeah, that will need to be designed first, because that is like a very complicated thing, even though that there's like only a tube with like holes on it. But the hole's diameter, spacing, location, the whole tube's diameter, all those things create the recirculation zones, which will dictate how well and efficient the ball burner is, and that will go a long way. Right. M dot. Alright, so let's read. I will have to put the data in. I don't know if you can process this. I think I didn't write this in. Oh my god. How the fuck am I going to do this? I think I will need to do matrices. I have the following data. No, can this print in? Control Shift Enter or Control Enter, Shift Enter. Fuck. Doesn't work. Don't process this 17% values as they are not. It was already the bottom of the barrel, so I will do this because I'm kind of lazy, to be honest, to fucking type in all the values. I mean, I could do that technically, but it's like it takes forever to fucking do it. I might get myself a coffee till it spits out these data points or like things. Alright, I will then stop it. First is temp, the second sec is PWM percentage. duty 15%. Then time in sec, and then the sure the total mass of the bottle. For example, at 16 sec, it alright, have to correct I didn't have it in the prompt, so it was my fault. Still faster than sucking with the values, because you need to create the matrices, then you need to correct the matrices, then you need to do the coding, all that, so it takes a lot of time to type in. And once that is being done, I can go and grab myself a coffee and a tea. So be right back. like it did something. Very well. So, alright. Alright. So we will have some this junk, ignore those rows. Is it still going? Alright. I mean, does it? Just curious to check. What the fuck? Alright, it is going, I guess. Alright. Just it didn't show in the thingy. Alright, then it is visible. Just curious. Okay. So, yes. Time total mass. Alright, we can create good old rows. This is temperature, this is duty, this is time and total, this is mass. We will be able to divide these. So we basically divide the. Do we have the first one? Oh yeah. Okay. So we have the first one. So we can basically divide the row 4 or column 4 with column 3, and we would get the per second mass flow. Ampron script. Alright. Code. Take the code. Alright, split the columns. I think I do not know how to fucking do this, to be honest. I think you basically put it into like a I don't know, fuel mapping. That's great. I think this is going to be called day 2 data. I'm going to put this here. Alright, we have this big fucking fat ass. I don't know if this should post to. Oh, alright. Yes, I think like this will make sense. This is going to be data, day 2 data, and then maybe just yeah, right. Alright. You can do this actually, this very interesting trick with Alt. You can select multiple rows in this, which doesn't really work in like other programs, or not all. Example, in the text bullshit, it doesn't work on TXTs, so it's pretty bad. So day 2. Alright. I don't know if this works or not. But it's supposed to. Nashgu. Alright. 1 times 48 value. Let's check the temperature. Or yes, the temp is supposed to be a fucking a big fat ass. 4.5 T is okay, and if we take this and save this, then we put it very close to 1. That looks like it was yes, I know. M dot. Oh yeah, okay. So oh, alright. For which we didn't get mass flow rate. fit the straight line MTA for a base slope A must slow M slope. Okay, let's see. Alright, do we have I do not know. Unique PWM size. We'll see if this works or not. I really hope he does. Right, it actually is pretty linear, as I said. Yeah, this R square bullshit is like a difference. It's like I think it's a method of like least squares, whatever. So basically, you take you take these data points. You take these. Which one are these? These grams, and basically you have like a polynomial, which is a where is this? Kind of like this. I don't know if I can zoom in. So basically, if you learned any math, you basically have like an x, which means that the x, where is this? Where is the? I'll go back to down here. There is this, which is basically a function, which is the mass flow. You have a times t plus b. Basically, this is the x, or t in this case, because the x-axis is the t as time. So basically, this gives us the a is a coefficient of the, I don't know how they call this in English. It basically gives you the angle. So if basically if you have 1 times t, then it means that you step 1 here on the x and you go up 1. So basically, if it gives you something like 34, then you go 34 up and 1 here. Basically, it gives you the angle, or angle of attack. I don't know what they call this in English. Basically, the how steep is the angle, or how yeah. The other one is basically the b. If I remember correctly, I think b basically pushes the starting point from the x above, I think, if it's that, because the normal would start in 0 0 in the origin point, whatever you call it, but then these are going to push it. I can't remember on either on the x or on the y, but I think it's on the y. So right, meaning that it pushes up or down. So it means it would be basically 8 times. I can't remember it correctly. I don't want to tell you like BS, but I think this is correct in the sense. And we want to create a polyfit, which means that if we take this correlation, meaning that we have this data that we get out of these points, basically we fit a thing on there and see how much deviation is there, because the points would be just like, you have like a line here. I'm going to draw it in Paint, because that's maybe a better, or maybe I have a better idea. So I have this, so take this and alright, so basically the points are going to be all over the place compared to the, let's say, to the brown line. But this is the mean, so basically if you put the how do you say this, adjust the line to it or something, adjust the spline to it, whatever, and the closer the number is to 1, the points are closer to the line itself, actually. So if it is 1, that they are exactly on the spline. If they start to become basically you would go lower than 1, basically you go towards 0, meaning that you have like 0.5, then they are all over the place, so that basically the distance from the line is going to be bigger and bigger, so it is going to be a rougher polynomial, meaning that you would need to fit not first hand, this is like a first order polynomial, you will need to fit like a second order polynomial, meaning that a squared t times t plus a times t plus b, and the like the lower the r, this r square or whatever the fuck they call it, this error function, the longer the polynomial needs to be, on the longer, how do you say this, the higher the order of it has to be. So for on the square, then third, then fourth, fifth, sixth, and so on. When you are looking at, I think it was CP, which is the gaseous coefficient, or I don't know what the name is for it, it's a constant pressure gas coefficient or something like that, constant pressure gas coefficient or whatever the fuck they call it, and basically it's like a 7 or 8 order of polynomial that you need to have to be able to calculate it pretty accurately. I mean, you can calculate it with like less of an accuracy with lower order polynomials, but you would need higher order polynomial to have like a good fitting. And it seems that we have long side tension here, but we have a pretty good polynomial fit for this PWM thing. I mean, I might have not told you that why actually we are doing this. Basically, we need these data so that I basically in the future, when I will run the burner, I will exactly know at 15% PWM, and this is of course for sure a given height. So basically you have like the pump here, it sucks, there is like a tank here that it sucks the liquid from, and it pushes up to a certain point, and this distance here, this is like a delta H, fuck you, so this is a delta H, which is going to give you a delta pressure that you can basically it's I don't know what they call it in English, but if I had to like mirror translate it with something, it would be like something like carriage height or something like that. Basically how high the pump has to pump the liquid up, and that's going to give the delta P that it has to overpower in itself, because it needs to you know, push against a given amount of delta P. So there is like this height which has a static pressure, and or to be honest it's a how do you call this, hydrostatic pressure. It's going to create a, so to speak, friction, a resistance here that the pump has to overcome, and the higher you go, the less mass you will be able to push through the pipe. But this is, and that is for a certain given amount of delta P. I don't know, I have noted it into the in the video that I have recorded it. I have basically streamed this I think like 3 weeks ago or something like that. So yeah, we have these pretty fucking pretty accurate. This is 100%, 100%. So it is 99.96. So 99% and 96. So 99.96% accurate data. This is a bit shittier, 79, but the rest of it is pretty accurate. You can see that we have a pretty strong correlation, and I think it is for all of them. So this is from polynomial to all of them. This basically will give us the accurate control over the whole burner, meaning that when I will tell basically set the burner to not be run by manual control, but like fully automatic, meaning that the computer will determine the amount of, I will set the value, let's say I will need to produce steam, I don't know, 100 kilo per hour or 100 liters, whatever the amount. Then we will measure out how much heat we need, and yeah, that will need to be like adjusted for. But if we know that we need to 100 liters, and we know the correlation inside the system, which starts with this, because you need to know how much fuel you pump in, and with like, if you want to really break it down, then the fuel, I mean, maybe I will draw it here so it's a bit better. So the M fuel will determine the mass of air that you need. That will determine, these two will determine the Q, I think, which is the total heat flux, meaning how much heat energy you put into the system. And I will have to measure how efficient the whole thing it is, which is basically Q in versus, or is it for Q out per Q in. This is mass flow, or we can use I think Q, which is, we can take this down basically, because that's like a constant in that instance, if I'm correct. So Q in per Q out, or Q out per Q in, that's going to give us the eta, which is going to be the efficiency, the thermal efficiency, TH, thermal efficiency. And with the thermal efficiency we will be able to determine the amount of heat that is useful. Basically the heat is useful will give us the amount of mass. This is going to be the, I mean, technically this could be, if we do not use dots, then we do not use dots. If we use dots, then we use dots throughout the whole thing. The dot is just there to mean that it is a flow. In this instance it is like a constant. We could use the dots everywhere. So M steam, basically fuel gives you the necessary air that it requires basically, and basically everything starts with the fuel. So when you want to control the process, you control it with the amount of fuel that the pump pushes into the burner, because the lower the pump duty is, meaning that the lower fuel it pumps in, the lower heat it produces, then the lower amount of not thermal efficiency probably will change depending on how hot the system is, but that is like a how do you say this, that's like an own plot, that it's kind of like, you know, it goes up then it goes down or something like this, with temperature and mass flow of like steam or something like that. I don't know, that this is not little t but big T. This is big T and this is like mass flow or something. I do not know the exact, but I assume something like this. So there is like a sweet spot that you need to hit to be able to produce the most amount of steam with the highest efficiency, and probably would have like multiple of these given eta. So with the better the or maybe even like this, I don't know, who the fuck knows. We'll have to plot these out as well. I have no fucking clue about this, just some speculation. But these are pretty this is like pretty certain that you need to do it like this. So yeah, fuel the basically is the the backbone of the whole system that will give you the amount of steam in the end, but it is not straightforward. It gives you step by step. And when you define how much fuel you put in, you will be able to know how much theoretical heat you should get out of the system, but that's going to be lost, or some percent of it will be lost, and that will be, we will be able to measure that with like heat, and maybe, I don't know, maybe with the steam that we produce. I don't know, maybe I'm going to put some volumetric flow there, and measure out how much liter per minute we or liter per hour we produce or cubic meter per hour we produce, and with that I will be able to calculate the thermal, and then basically with the thermal to a given point we can maybe make like these little plots that we can use to actually then produce the given amount of steam that we will need to use in the Fischer-Tropsch, because the Fischer-Tropsch will need steam to basically initiate. The burner is there to produce steam to heat up the Fischer-Tropsch to then produce synthetic fuel, but this is necessary for it to run, but then you will be able to basically recirculate. The Fischer-Tropsch will produce its own steam because it is exothermic, and you need to cool it, not heat it, to be able to run, because it would overheat in itself. So yeah, so then it would basically turn the the table, and the Fischer-Tropsch would produce the steam, and that you could use to actually run the pyrolysis with heat, like I don't know, 400 degrees. I think water caps out at something like 500 degrees or something like that, and you cannot really heat it up higher than that even with a lot of pressure, because it's going to get to super heated state or some shit like that. So yeah, supercritical state, kind of getting like into plasma or some shit, not thermal plasma, but like supercritical, so that there are like free atoms, and the atoms fall apart to ions and all that bullshit. So I do not know much about that, but you don't want that at all. Polyfit m.min. Let's see what we can achieve here. Hello? It is circling, so I assume that either it haven't run, probably it's making the plots right now. Yes. Pretty good. This is what I meant about the dots and the polynomial fit. This is like a second order, so it is like a poly order 2. So this is pretty nice on it, pretty straight. Alright, print the equation. Highest order first. With this we will be able to I mean maybe where the fuck does this start? And polyorder 2 polyfit n, which is the first line. Northwest, where are you? Northwest. Oh fuck me. Oh, here it is. Alright. I think it was the Alright, then it don't work. Fuck off. How do you call section break, I think. Yeah. Alright. Alright. I think oh, fuck off. Alright, alright, alright. Okay. This is not function. Smart event. No, I don't think this is it. I think section break. Yes. Alright. This looks a bit better. Okay, run this bitch. Have a bit of coffee here once that's been done. We can see here that the polynomials to PWM polynomial coefficients. Basically, this is the second order, so the x on the square or t on the PWM on the square in this instance. This is the first, so the PWM on the first, so just PWM, and this is the just the basic number, so it would look something like this. So to do the times PWM squared plus to be exact minus this times PWM plus the basic number and the all in grams per second. Alright, quadratic is good enough, and then we compute the r squared to the PWM fit to see if we have done it. Keep it simple, but I think it will give us good r squared. Fuck off. Does it have? Can we? Alright, section break. Alright. Of course. Let's see. Mm 9839. That's pretty good global fit. Interested if I give it 3, so polynomial 3. But the 99.53. That's a pretty fucking straight. Pretty fucking accurate one. Yeah, 99.53. The cubic is sure better, but like, I mean, fancy enough. Keep it simple. Let's go back to 2. It's enough for us. Don't want to overload the computing power. I don't know how accurate we would be needing to use it. Alright. Correlation later. Yes. Can I do this? I'm just interested. I think it's supposed to be like so. Right. Alright. Alright. What do you call this quadratic? I think 39. The cubic ones. 99.53. I have no clue about this, I'm not gonna lie. Yeah. Yeah, we have seen that the cubic has this is where the fuck is this? Would be good old quadratic back. Still pretty nicely fitting it. I will come back in a few minutes and do another batch of fun. For now I will take a break and have a meeting.